Yes, it's for me also a pleasure to be here in Belgrade. It's the first time, and so I agree with the other speakers that we are really delighted. And thank you for this invitation, especially to Professor Dimkic and the colleagues of the Belgrade Waterworks. As I said in the discussion, I'm a colleague of Heinz-Jürgen Brauch, working for DVGW, which is a technical and scientific association. The main focus is on the developing of technical standards in the field of gas and water supply, but we also give guidance for the suppliers regarding emerging topics which are relevant to secure water supply. And in this frame, we also started a discussion on climate change mitigation and adaptation as well. In the following talk, I would like to give you an overview of the discussion, which has started and which is still going on, and give you an overview and some insights of the recommendations we have elaborated for our members to tackle the issue on climate change and water supply. Let me start then with a short introduction, then continue with the impacts of climate change on water supply, and then I would like to describe the consequences and options for water utilities. And finally, I'd like to suggest some aspects for the way forward. Yes, climate change, and this has been reported many times, this conference have been in the focus of public attention for many years, and as the colleague from Austria, Johannes Krat, just described, also the European Commission is planning to present the so-called blueprint to safeguard Europe's water resources in 2012. And in this context, the DG Environment is also carrying out an evaluation of the European water policy and also focuses on climate change and the vulnerability of water resources. Let's have a look on the impacts of climate change on water supply. Climate change may result in the more frequent or intense occurrence of familiar phenomena that may also spread to other regions. This may include more frequent or intense periods of droughts, heat waves, and rainstorms in regions that so far have been affected by these phenomena either not at all or only rarely. However, the water supply industry will not be confronted with vague unknowns, but in general with phenomena it is experienced in coping with. Don't understand me wrong, this is not supposed to be understood as an all clear, but rather meant to encourage a proactive and unemotional discussion of the effects brought about climate change for water supply. Regional projections for concrete quantitative parameters are still uncertain and can be made only within relatively wide boundaries. The degree of uncertainty is higher still if you want to determine on the basis of various climate factors like precipitation, temperature, evaporation, the changes of parameters like, for instance, groundwater recharge or runoff regimes in river catchments. So first, let's have a look at the changes in water availability. And there, let's have a look on groundwater. So the following consequences in changes in water availability became apparent. On the one hand, it is assumed that we will have a permanently declining and seasonally diminished or absent groundwater recharge, which leads to a sinking on the water table. Especially very small groundwater systems or springs, which are fed by small or near-surface aquifers, are less capable to buffer variabilities in precipitation. On the other hand, in regions where groundwater recharge takes place almost during winter times and where winters are getting wetter, average groundwater levels are expected to rise. This may cause waterlogging and damage to buildings. Changes in water resource availability may also result in major groundwater quality changes. For example, a non-dilution of contaminated groundwater may lead to higher pollutant concentrations in raw water. So this is the case for groundwater. Let's have a look at lakes and reservoirs. Regarding lakes and reservoirs, there could also be a seasonally and intermittently sinking level which could diminish raw water availability exactly in the time where there are peak demands. This may result in smaller depths of storage volumes suitable for raw water abstraction and a smaller portion of cold deep water, the so-called hypolimnion. Beyond this, the capacities to buffer polluted inflows and water abstraction control options may be compromised. As well, rainstorms may adversely affect raw water quality as they may cause erosive runoffs and an increase in spillovers from separate and combined sewage systems, which could lead to an increased input of sediment and particle-bound contaminants and microorganisms. This could also be the case for watercourses. So let's have a look at watercourses. The risk of flooding increases with the rising frequency of rainstorms. Floods may adversely affect groundwater quality and mobilize dangerous substances, for example, from industrial brownfields. Extremely high water levels may submerge bank filtration systems and thus directly pollute raw water. Low river flows may lead to higher concentrations of pollutants and affect raw water quality. This is relevant also when river water used for artificial groundwater recharge or bank filtration. So this was the topic on water availability. Let's have a look on the effects of rising air and water temperature. Higher air temperatures could increase the vertical temperature gradient in lakes and reservoirs. As you know, there is a thermal stratification, and this could become more stable, so full circulation, which is required for the renewal and oxygen supply of the hypolimnion, which is absolutely crucial for raw water abstraction, could occur more rarely. So full circulation may also decrease in length and may even stay away for good in some cases. Higher temperature generally also accelerate biological and chemical processes in water bodies. This tends to affect raw water quality as well. The extent of the impact, however, also depends on other parameters such as the availability of nutrients and oxygen. This may foster the growth of algae, so that algal blooms and the formation of odors and flavors at the same time, as well as a release of bacterial toxins may occur. Higher air and also soil temperature may also lead to higher drinking water temperature in the distribution network. Whether higher temperature increase the risk of microbial growth and contamination depends, and I think that's very important to mention, it depends very much on the general condition and operation of the supply system. But there are also indirect consequences. For example, when you look at the boom of the cultivation of energy crops for biofuel production, agriculture is going to get more and more intensive with a growing demand for irrigation, the use of fertilizers, and the application of pesticides. So I would assume it's only a matter of time to discover the impacts on water resources quality. Extreme weather events may also lead to crop failures or even ruin the entire standing growth, causing plants not to absorb the fertilizers applied before and all the fertilizers to remain in the plant residues, which may result in massive nitrate pollution of groundwater. And another point may be conflicts about the use of locally and regionally available water resources. They could arise. Locally and temporarily, water resources may not be enough to satisfy the demand of all users, water suppliers, households, farmers, commerce and industries in the region. Another point showing indirect consequences is when you have a look at the very, very dry and hot summer in 2003, when peak demand increases very, very intensively. As a result, there was a gap between the average and peak water demand. And this situation even became worse in regions with decreasing average water demands caused, for example, by a population decrease or a change in the industrial consumption. So these are all challenges and circumstances for the water suppliers they have to face, and they have to find new solutions for the design, construction, and operation of the water supply systems. So let's have a look at the options for water suppliers to tackle climate change and effects of climate change. In order to identify suitable adaptation measures, it would be good that water suppliers analyze their individual situation comprehensively and ask a couple of questions. And, for example, these questions could be: which impacts and consequences will affect my supply system? Which assets and processes of the supply system are particularly sensitive to the expected impacts? And which adaptation options do the ongoing operation schemes and the established management tools really offer? And what needs should be considered with regard to future investments? So then, a continuous integration of the findings obtained when giving responses to these questions into all planning and decision-making processes of the operational is very crucial. And on the next slides, we could have a look at, I would like to give you an overview of potential adaptation options regarding the different steps of the process within the water supply. And when we start with the water resources, it would be good to assess trend analysis and draw up long-term availability projections. Then to adapt monitoring networks and programs area-specific to enable the assessment of potential quality changes, and to apply to an integrated water resources management, both quality and quantity, and to secure drinking water supply with regards to the official spatial planning and water resources planning. Regarding abstraction, treatment, and network operation, it would be an option to establish redundant abstraction systems for a more flexible combination of different types of raw water resources and abstraction technologies. Therefore, it would be good to create networks to look for additional raw water sources, to integrate neighboring supplies, or to just check the connection to regional water supply systems. Another option is to adapt wells and pumping facilities to changing parameters. So far they occur and the parameters are changing, for example, the water table, and to adapt water treatment to expected new or changed raw water qualities. Regarding storage, one option could be to create larger storage capacities in waterworks and network to ensure that supply meets growing peak demands, to adapt network inspection and flushing schemes, and at least keep water losses permanently low as possible on an economically based criteria. And then, at least regarding organization and management, I think it would be good to adapt organizational structures and management processes to the expected changes to be able to manage risk and crisis. Let's have a look at the way forward. There is no one-size-fits-all solution for climate change adaptation. I think that's very important to state, and there is a need for adaptation, and the scope for action will refer from case to case to the natural conditions, to the technical structure of the supply system, and as well to the interaction with other factors such as societal and economic development or concurrent industrial and agricultural water uses. And then a lot depends on the utilities' willingness to actively address climate change issues and to rely on both its own and as well external know-how. There are uncertainties of projections, and the knowledge about the increasing variability of climatic conditions need to be very, very systematically analyzed and considered in the management of resources, as well as in the operation and design of supply structures. And then, and this is at the end really a message, all societal stakeholders need to be made aware of the fact that the protection and sustainable management of water resources is an interdisciplinary task to which the water industry, the water supply industry, can contribute its share, but which it can by no means accomplish and find solutions on its own. So, that's it. Thank you very much for your patience.